Welcome back to the course on symmetry, stereochemistry and applications. This is the 10th week of this course. So, in this course now in this week we will discuss about a few well known chemical reactions, and we will discuss about the reaction mechanisms of those reactions. So, today in the first lecture I am going to start discussing about the well known diels-alder reaction. This reaction is known since 1928. German scientist Otto Diels and Kurt Alder discovered that the alkynes or alkenes with electron withdrawing groups group, we write it as EWG, add to a conjugate diene, that is a compound which has two consecutive double bonds like this, to form a 6-membered ring. So, the reaction that they proposed or that they discovered is the following. When you have a diene like this, we have two double bonds. A conjugate diene is treated with a double bonded compound with an electron withdrawing group connected to it. So, this compound is called dienophile, which means a dying loving substance. So, when you heat these two compounds, what happens is we get a cyclic product as I am drawing here. This product is called the diels-alder adduct. Right. So, this particular reaction is also called a 4+2 cycloaddition reaction. This is a 4+2 cycloaddition reaction. As a ring is formed by the introduction of two sigma bonds and breaking pi bonds. 2 pi bonds rather, or rather 3 pi bonds. So now what happens is 2 pi bonds are converted to 2 sigma bonds, and the reaction takes place in a concerted process. Which means the breaking of the pi bonds and the formation of the sigma bond takes place simultaneously. So what we are seeing here is that the pi bonds that are being broken are those 3, and a new pi bond is formed here in the CC bond in between the diene molecule, and 2 sigma bonds are formed here. 2 new sigma bonds are formed, 3 pi bonds are broken. So technically 2 pi bonds are converted to 2 sigma bonds. And what is the important aspect here? The important aspect is that the reaction proceeds with a dienophile which has an electron withdrawing group. So this diels-alder reaction is like a nucleophile electrophile reaction. Here the diene is electron rich and the dienophile is electron deficient. The presence of electron donating group on the diene and electron withdrawing group on the dienophile favors the reaction. So let us see this with a few examples. Suppose we have cyclopentadiene and we are treating this with a compound which has a CC triple bond and has the ester group on each of those carbons connected to the triple bond. So the cyclopentadiene is called the diene here, and this diester is called the dienophile. So when we heat these two compounds in a solvent, what we get is a reaction in which the bond migration happens like that, and what we end up getting is a compound which is this one. So, here this was our 1 and 2, and that 1 and 2 are here, and 3 and 4 are those two which are here. So, this is called the diels-alder adduct. So, similarly, if we have a diene which has methoxy group, which is the electron donating group or EWG. So, this is a diene with electron donating group, and you have this cyclic dione, cyclopentene dione, which is a dienophile with electron withdrawing groups attached to it. Then a similar reaction can take place and a new compound will be formed on heating it in a solvent. So, the product that you would get is this one. Right. So, this is the diels-alder adduct. So, hope you can now follow what exactly means by a diels-alder reaction. So, now let us try to understand the reaction mechanism of this diels-alder reaction. So, as I already indicated using the arrows which indicates the movement of electrons, reaction happens in a concerted mechanism and a product is formed. An adduct, which is this, is formed. So, what happens here is that the pi bond of the diene, which is drawn here, if I try to draw the p orbitals on that, and the corresponding p orbitals dienophile, they interact like this and they will form the product with a double bond being shifted and a pair of new sigma bonds formed between the overlap of these two molecules. So, now if we try to see some of the examples of diels-alder reaction, some well known examples of diels-alder reactions. The simplest one that one can think of is a butadiene reacting with butanal, that means ethanal, which essentially gives you a simple product like this. Example number 2, this butadiene is reacting with, sorry, this is propanol. This trans dial is treated with 1,3-butadiene. The product is only this one. What does it mean? The trans geometry in the dienophile is maintained in the product. Which means this reaction maintains the stereochemistry of the substrate and does not allow any change in stereochemistry of the substrate, which essentially indicates that this reaction happens in a concerted mechanism. Now, if we have a diene with electron donating group on that, that is a methyl group, and we are treating it with this diketone, cyclohexene diketone, the product that we would get is this one. So, similarly, let us take the fourth example with this diene, which is treated with a C triple bond C compound with CO2 ET on either side. The product of this reaction would be a bridged compound, and that would look like this. So, these are some reactions which essentially indicates that this particular reaction, that is diels-alder reaction, is a concerted step, and it gives you a cyclic compound as a final product. So, now the question is, what is the stereochemical requirement of diels-alder reactions? So, the first point that one should understand that it is a concerted mechanism. Through a cyclic movement of 6 electrons through a cyclic transition state. The transition state must have a geometry that allows for the overlap of p orbitals of diene with the p orbitals of the dienophile. What is the advantage? The concerted mechanism allows us to predict the correct product and for a suitable arrangement of diene and dienophile is required. So, for the diene we should have S cis conformation, which essentially means that there can be a butadiene with S trans conformation. This S trans is in equilibrium or with the S cis conformation, with S cis being the less stable conformer. So, this S cis conformation is required for the diels-alder reaction to take place. So, as I indicated in the previous slide, that this S cis conformation, when reacts with the alkene or the dienophile, the transition state that appears looks like this. And the p orbitals are such that they can overlap efficiently. So, this stereochemistry is absolutely required for a successful diels-alder reaction to take place, and that is why we should always heat the solution to bring the S trans conformation in the solution, and then the reaction takes place smoothly to give you the diels-alder product. So, when we try to draw a set of dienes, let us see which of these dienes will undergo diels-alder reaction. See, this particular diene has two double bond always in S trans conformation, and this does not undergo any diels-alder reaction. If we take this butadiene with 2 methyl groups coming very close and having steric congestion, this will have in case of S-cis conformation, this will have steric strain. So, the reaction will be slow. On the other hand, if those 2 methyl groups were on the other side, the rate of the reaction of that compound will be equivalent to 1,3-butadiene in its S trans conformation. Then, if we think of a diene which has 2 methyl groups connected on carbon number 2 and 3, this will have a faster rate of reaction, and when we have a cyclic compound like cyclopentadiene, where the conformation is always locked at S-cis conformation, then it is very fast, which essentially means that this cyclopentadiene will always try to stay in its diels-alder adduct condition and will not be available as a monomer in your reaction medium. So, from here we will continue in the next lecture. Thank you.